So we got this result for integration. Converting double integral into a integrated integral or repeated integral, and so a double into two single integrals. Even though the first one will have parameters, which means that we are in a place very similar to partial differentiation. So when you remember you differentiate with respect to say y, then after the differentiation, and then you do the same thing with respect to the other variable while keeping the other variable constant. Okay, so this is called the Propagation theorem. Okay, and certainly worth mentioning also that the order then doesn't matter. So I could integrate with respect to x first and then y, or vice versa. So I have the parentheses. So dx here first, from inside out, dy, cd. So that's the part of the statement of the theorem. So under the assumption, naturally, that f is integrable to begin with. So then the implicit conclusion, so that's the assumption that f is integral, but implicit conclusion is that also when you fix y or x, the resulting function is also integral with respect to that variable. So these are three different concepts interacting with each other. Integrability with respect to each of the variables, and secondly the double integrals. Okay, so the Riemann sums, the limited Riemann sums. Okay, so and then this was the example of how it is done. It is, as you can see, fairly uncomplicated. Certainly no more complicated than partial differentiation. Okay, so any questions about this little computation? So just careful not to think too much about, like, in terms of anti-differentiation. So it is possible to find an antiderivative and then find antiderivative for the antiderivative, and only then deal with the limits. That might mess it up. So the way it is carried out is literally until you're done with the what's circled there inside the parentheses, treating the function as if it depends on y only, and x is a parameter, and then the end result is a number that depends on y. Okay, so which is or rather does not depend on y anymore. It depends on x, and so that's what has happened here. So what was circled in the beginning is the end result is here. Okay, so on the part of the outside is the same. The integral 0 to 1 on the left and dx on the right, and the end result is literally a function of x, and that was illustrated also numerically over here. So we went horizontally, rather, well, to be the opposite. No, we did horizontally. So the integral was with respect to y, producing all of these values in this column, which creates a new function with respect to x. Okay, we plotted on right, and then finally we integrate that last function as well. Okay, so once again, integration. The first step is kind of bigger because it has both x and y. You have to be careful to know whichever you're treating as a variable, and then do it for every one of them. Okay, and then the result is a function of the remaining variable, which is then there's no confusion. Y has gone. It is gone now. Okay, so y is gone. Okay, so it's different from partial differentiation, because in partial differentiation you're still left with, but by partial differentiation I mean the second degree partial differentiation, and in fact for that mixed partial differentiation, which is still to be discussed, when you differentiate with respect to x and then with respect to y, what happens? Something like that happens, except we're going in the opposite direction. Anyway, so this is really not, we cannot take this far enough even to revisit this issue. Remember, the whole topic was started with approximating the volume of a sphere, and that cannot work. And then we proceeded on when we developed the actual theory. The domain was a square or a rectangle. Okay, and then everything has been worked out, but not really the possibility of a non-rectangular domain. So that's still to be taken care of. But I think we'll postpone that until later and instead move to dimension 3 first, and the triple integrals. Okay, so the reason is that when we started this topic, it follows the ideas of calculus 1 and integration of Riemann integral of numerical functions, but it's been so long that it's as if you were learning it again, and that transition might be lost. And the transition, the step, is what's important here. Not really dimension 2. There is nothing special mathematically. Dimension 2, and then we go to dimension 3 once again. So it seems we are living in a three-dimensional space, but it's really not that important. We are actually going to pass it and keep going. So the step of raising the dimension is what really matters. And so that's what just has happened. But I want to do it one more time. So then we would know that we can keep going non-stop. So we will go from dimension 2 to dimension 3. Okay, and see if there is any difference. There is really no big difference. Okay. So first of all, functions of 3 variables. Nothing special about that, algebraically speaking. So triple integrals, but also functions of 3 variables. There is really nothing special about these. So this is just a function of when we list x, y, z here, the variable xy squared minus 0 cubed, whatever. Okay, so 3 variables are listed, and the idea is very straightforward. There is that doesn't really take a lot of thinking to see that you can pile up variables as much as you can, and there is no stopping to it. It is when you move on to concepts of differentiation or integration that require some kind of visualization or interpretation of metaphors that there's some kind of issue here. And so that's the challenge. So we already understand triple functions of 3 variables, and the only little bit of a challenge is that we just a minute ago we had this. So this is z equal f of xy. The z was the dependent variable and xy independent, and now suddenly we're switching to well, let's say u is the independent variable. Z suddenly becomes the dependent variable. It's just the comes from our xyz space. And then we're reusing it as we're moving on. And then at this point, there is no 4th dimension to be visible. So we'll have to manage that somehow. Okay, so that the formula is easy now. Visualization of functions of 3 variables is let's visualization. Okay. Well, you can guess. So if this is a function of 2 variables, what is the visualization of a function of 3 variables? Right, then the question I'm asking actually, what would the data look like?
It would be a 3-dimensional circuit. Or
3-dimensional what?
Cube.
A cube, or it's still an array, a technical term from computer science, an array of numbers, and a box, if you prefer to think about it as a metaphor. Okay, let me first copy this. Okay, so let's try to do that, and Excel does it. Certainly, you can see it's 2-dimensional, but it's not. Okay, what's going on here? So I'll do it. What happens? Okay. works and then it doesn't work. I don't know what that is. Maybe I do. Okay. Okay, so, well, I don't know what happened. Let's try to close it. And we'll try to close this one too. Save. Once again. Okay, so I just want to visualize. I don't follow this. Okay, so. Okay. Okay. No, kill it. Kill it. Okay. Okay, so the data will be a 3D array, which how do we do it with Excel? We're going to add layers, so or sheets over here, and so you can have as many as you like. But before that, let's take care of the very first sheet. Okay, the one that we're going to copy. Okay, so that is my graph. Okay, so there should be three variables. This is the you see the formula for the hyperbolic paraboloid. It refers to x values in x and y. Okay, so we have to introduce the variable z. And I will. Except I have to refer to a certain cell where that z will be located. And the way I choose it to do is, let me erase this. It doesn't apply anymore. I will put z here. Okay, so this will be z. Z right here. Okay, so say 0. Okay, and so my formula will be for each layer will be referring to this particular value of z. And then as I move to the next layer, I will be changing the value of z. That's all. Okay, so for example here I will be referring to say minus that entry are 6 C4. Okay, so see that's the reference. Okay, so it's not going to do any difference make any difference because it is 0. Okay, so these the values, and now I can create a function. Create a I'm sampling, right? So this is a sample of a function of two variables. But if we have more data and more domain becomes a box rather than a rectangle, right? So there will be more of the same. And so this is what I do. I'll just copy make another one. And another one, so let's make it here. Okay, you can actually see what, well, one more. You can actually see the values up here. So in fact, I go back to the original, I put 1 here in order to match things. Okay, so that in parentheses, number here will be simply the value of z. So 1, z1, z2, z3, z4, and this is equal to 5. Okay, each of them will have a different values as long as as soon as I enter it. Or so, for example, I put 2 here. Okay. Okay, so the picture changes slightly. This is z equal to 3. Okay, z equal to 4. And z equal to 5. Well, what I should have done is z equal to 5. I should have done the wrong picture, but okay. So, but I hope you can see what's going on here. So these are 5 different arrays of numbers. Imagine then they're stacked up, so just like they showed over here. So one under the next. So it will be not a rectangle of numbers. It is in fact a box filled with numbers. So certainly where they come from, our function is defined on that box in each real triple of real numbers within that box, and that has been sampled in all those locations, and this is the result. Okay, the only question remains is the meaning of these pictures, of these graphs. So they still look like graphs of two variables. Let me change. Okay, so that makes more sense. So okay, so what is the meaning of this? What is the meaning of this graph for our function of three variables? So remember, we had one description, but the visualization of function of three variables, and that was the level surfaces. Remember, but the level surfaces are just like level curves, are acquired by fixing the output variable. Okay. However, here in each layer is fixed one of the input variables. Z is now the input variable. So they are like these. This is in the xy plane. We're seeing the xy plane, and then Z is going from sheet to sheet like this, changing from 1 to 3 to 3 to 4 to 5. Okay, and that creates that box. But and then within each layer we plot what. The vertical variable here is not Z. It is in fact variable U, the output variable. So in other words, these are just like those functions that we did partial differentiation with. When you fix one of the variables, and when you have function of two variables, you fix one, you have function of one variable. Not so easy with functions of three variables, because when we fix one of the variables, that is Z. We end up with still two left, and that's why the graph remains to be a surface. Okay, so a bunch of surfaces which might intersect, and they do not behave too well. They might not match. Let me make another point. Unfortunately, once again, I have to change the type of this series. Okay, so what I'm trying to do here, well, there is actually the third interpretation of our third or second, actually I'm not sure, interpretation of the four, or metaphor for functions of three variables, and that is a function of two variables, which gives a terrain, okay, and the third variable time. Okay, so then it's not a terrain, but rather what is the terrain that is changing with time? So can you think of a grade? So once again, a terrain changing with time. What is that?
Wait, what is the question?
What
do you mean?
Terrain that changes with time. That's also terrain that changes with time, like
Like
this.
when you're driving
No, you're not driving. No, mountains, they don't change. You are driving, that's the change, but they are changing the
Ocean
function. Waves, right? It's like waves going up and down. So they are all curvy, right? But they are not remain the same with time. And that is the time is the third variable. Okay, so it's roughly, this is how you can think about it. I'm trying to demonstrate this like this. So time starts to progress. 1, 2, 3, 4, 5. So these are the waves. Okay, you certainly can think of more complicated functions, and you can see more of this. So if you study, for example, literally wave propagation, you would end up with a propagation in a three-dimensional solid. Then you would be, or a three-dimensional medium, you would be studying a function of three variables. Wave propagation starts with dimension 1. You have time, and you have a string. So that will be just a one-dimensional string. And then two-dimensional, that's a drum. Okay, and the third dimension is time. But then the more general Case of wave propagation would be a medium such as air, a three-dimensional medium. Well, hold on, let's make it four-dimensional. Yeah, okay, so that's fine. So this is actually a drum or a wave of the ocean. And then the next step, then, well, that makes a good point here, is that the next step is wave propagation in space, such as air. So the solid itself, the medium, is three-dimensional, and the time is the dimension 4. And the output, these are all input variables. So the location, 3 numbers, time, 4th number, and the output is the 5th number. So you have a function of 4 variables. Okay, this is just still the drum, like it goes up and down under the producing the sound. Okay, so so this is sample function of 3 variables. Really, what we are after is integrals. And so what we could I'm not sure if there is any good interpretation of the integral 3D integral for when you're talking about oscillations. But if we go to the original metaphor, and that is, let's go to the metaphor, which amounts to either area, area and volume, which we already have seen. But what they have in common is the weight, or the mass, if you like. So we start with dimension 1, and what we're talking about here is a uniform lamina. Well, it is, lamina is uniform. So a uniform thin object, and with uniform thickness and uniform distribution of weight. So in other words, uniform density. And then the area in the integral, area is equal to the mass. So you can just think of density being equal to 1, and that's what we get in dimension 1. Okay, so that's the interpretation, the metaphor for the integral of a numerical function. Now, dimension 2, so we have this terrain, but sometimes it's better to think about it maybe like a sandbox, and which is filled with sand, but the top of it is curved somehow. Okay, and so once again, the situation is similar. We have all the dimensions measured. Okay, so the density is again say equal to say 1, and now volume is the integral, the double integral this time, and it's still mass. Okay, right? So because the density is equal to 1, the volume and mass is the same thing. It is when we move to dimension 3 that becomes harder, because we have to use all the 3 dimensions here already. So what we end up with, we are looking, as we have decided, and we will originally looking at a box. But then once again, let's not think about waves. Let's think about mass and density. So it will be a box, but the density will be non-uniform. So non-uniform density. We were looking for a good, kind of familiar, tangible interpretation of these integrals. So the function will be, let's set the integral aside, but the function is defined in the box. So every location here is our domain. Okay, and then we assign to each point in that domain a number. That's what the function is. So every location, a number. What is that number? The density. And the density this time depends on the location. And then now the volume is out. The volume is not interesting to begin with. It is a box. Okay, so and then the integral, this was triple integral, is mass again, or the weight. So to see that we do the same as we did before. We divide it into little pieces so small that they're within each of those little boxes. Within each of these little boxes like this, you might assume over here that the density is uniform. approximately it is. Then the mass is what it is, will be the volume of that little box times the density. The density, once again, is constant. Okay, so what you're looking at the very bottom, we're talking about the terms of the Riemann sum. Well, let me, for convenience, let me change the order here so it will be more recognizable. So it is, in fact, density times volume. So this will be dx dy dz. Deltas. For the time being, these are all deltas. We're talking about Riemann sums just yet. So it will be delta x, delta y, delta z, the dimensions of that little box, and this will be f of x, y, z. So the function f is literally our density, okay, depending on the location. We sampled our location. At some point x, y, z, we have a little box around it. We assume that the density within that box is constant, equal to this number. Then to find the mass of that little box, we multiply the density by the volume, and that is our mass. And then what do we do next? Well, we add these together, and we create once again a Riemann sum. This time, you see how things are multiplied, and we have then, because the array is three-dimensional, there will be three-way summation, and then as we take the limit, we will end up with a triple integral. Okay, so that's the transition. I hope this was more straightforward because the metaphor is almost exactly the same, uniform density, and we're just looking at the object sort of kind of a zero thickness object, while the other one is not. Zero thickness has some thickness, and that's why you end up with a double integral. And this one, the metaphor is slightly different because we're trying to stay within our three-dimensional space, and then the metaphor becomes where is the fourth dimension? And the fourth dimension is either time, could be density, or any quantity. Any quantities would be pressure, temperature, anything like that could be. But if we are talking about integral, the easiest metaphor, I think, is the density. So the density, and then you end up with a mass. So it's like so if this is a sandbox, this is a piece of plywood or metal, very thin one, and so that's why we only need the measurements on one side to determine its mass. Sandbox, uniform, all the same. This one, maybe it's a box and filled with maybe gas, and gas has different density in different locations. That's why you have to integrate to find the answer. The visualization, once again, either the way I did it over here, so each layer has a function of two variables, or so it's literally like you are in the three-dimensional space. You are trying to find the density. You pick one layer in this room. Okay, so and then measure within that layer, measure the temperature, for example, temperature or density, and then plot it. And then that's how you get all these 5 graphs here. Okay. In the meantime, when you get them together, you have this. Okay. So, all right. So this part might be harder ultimately than the algebra itself. It's well, the algebra itself certainly getting worse and worse from single summation in the Riemann sum to double summation in function two variables. Now it's triple summation, but at some point we should be able to avoid the cumbersome notation of 3 dimensions, hopefully, and you just realize there's one summation at all. Okay, so let's set it up one more time, the triple integral from scratch. So we have a box, u equal f of xy, xyz, defined on a box, AB cross CD cross PQ. in the 3 dimensions. Okay, so A, B is towards us, the x dimension. CD is the y dimension that is to the side, and the vertical dimension is PQ, that's positive. Okay, so then we do partition. A partition. In fact, you probably could do a partition for each of the rectangles. Not probably, definitely for each of the rectangles. For each meaning these 3, for the 3 intervals. Okay, so if we put it this way, then we realize that if we go up in dimensions the next time, we'll know what to do already, right? So this is this is calculus 1. This is just the recent double integrals, and now we are moving on to the next one, dimension 3. But it's still every time both the sampling and the dimension and the partition will coming from the partition of an interval. Okay, so of each of these intervals. And then if we will go to dimension 4, we know that once again there will be one more interval over here, and it will have to be partitioned as well. Okay, so partition, say A is equal to x naught, we're doing the same thing. Xn is equal to B, and then y naught, this is C, y1. So these are the endpoints, y, let's say n capital is equal to C, D, and here P is equal to Z naught, Z1, Zn equal to Q. Okay, so these are the endpoints. Endpoints of those partitions of the intervals, but in reality what we make them into, they become we combine them together, say x1, y3, z7. What is it? It is a corner of one of the boxes. Okay, so we cut it into, this is now a 3-dimensional thing, so one of these points might be given by 3 numbers, and you know that if you have n, and n, so you have n cubed corners, or they also known as the nodes. So the nodes of the partition, you can think about like what is it, like like a wireframe, 3-dimensional wireframe. So squarely, like a check line paper, squares everywhere, and then it's used for every layer. And then you go not only horizontally but also vertically, and it is certainly very rigid construction. Okay, and then the sampling. So next is sample. So you'll have what's the letters I'm using here? S N T N U N. About B N. Okay, so within no, the indices have to vary here. I, J, K. In each box. So this is my box. Okay, a little box. No, that's the big box. The little boxes that we divided into are here, like this. Okay, and they're throughout like little bricks. Of little bricks, you make a big, you build a big. What is it? A box of those bricks. Okay, so anyway, so these are sample points. What do we do with these sample points? We evaluate. We sample the function. We use them to sample the function. So we take f of s I t j b k, Okay, each ijk run between k and I, between 1 and n. Okay, and then we multiply each by the volume, once again, as we did. So delta xi, delta yj, delta zk. Okay, and then we have a triple summation. I'm not going to do triple, I'll just go with the three variables I, j, and k like this. So that's the Riemann sum. Okay, there is really no point to go beyond this. As you go to dimension 4, you can imagine that there will be more commas, there will be more deltas, there will be more sigmas, and they, at some point we'll just have to develop a better notation, multidimensional notation, in order to handle those. So for the time being, we'll just this will do. Okay, so here I, j, and k are between 1 and capital. Okay, so in other words, we have subdivided. I don't think I have a picture of that, so let me try to attempt to make that picture of the box as the big box that we have had from the beginning. And then what happens is, so each of the three dimensions is divided into thinner ones. So say, which one's which? Let's say this is x, and then I divide x first. Okay, so I start certainly on the x-axis, and then I'm slicing and cutting this piece of cheese into cheese cubes, I think. Okay, so that's division of x, then I do division of y, then let's say this is y, so once again I divide. Okay, so this is the division. And then finally I go with z, and I divide as well. Like this. Okay? So whatever it resembles the most for you, that's probably the best metaphor. The cutting itself is possible. So once again, if it is a non-uniform material and you cut it into smaller pieces, well, I mean you're after the mass of the object, so certainly you can just take the whole thing and weigh it. But hypothetically, if you don't have an actual weight or scale, you could. What we're talking about here is suppose you know the density. You can measure the density. So you cut it into small pieces. Each of the small pieces has its own density, and then you multiply that density by the volume of that piece. You cut out. Hopefully, it's the same size, but not necessarily. And then you just then add them together. So that gives you an approximation of the mass based on this computation, and then you finally take the limit as n goes to infinity, and that gives you the triple integral f. This is the shortest notation, so function is f. dv indicates that it is about the volumes. I'll put b over here because it is the box. B stands for the box, and this is, let me put b over here to tell what it is. It is a box with these three dimensions. Okay, so that's my triple integral. Triple Riemann integral. Okay, so everything once again reappears just like in dimension 2. And for double integrals, all the properties in dimension from numerical analysis to calculus 1 reappear. They have to be just handled carefully so we wouldn't. Some of the words have to be replaced. For example, distances are replaced with areas, or the lengths are replaced with areas, and similar things. Well, let me go back for a moment and see where those properties are. Hold on a second. The properties being, we talked about, number 1 was the sum rule. Where are they? Okay, the sum rule, right? So the original rule is here from dimension 1. Then we move on to sum rule for dimension 2. What's the difference? Not a big one. So dx is replaced with dA, right? Single integral to double integral. The biggest transition is from the limits that put at the top and bottom of the integral sign. Right now they simply replace with in a more subtle way to do it. We just refer to R, which is our rectangle, or whatever that rectangle is. It doesn't matter whatsoever for every rectangle. The plan works out. Okay, and then same for constant multiple rule. Okay, so once again, there's a constant multiple rule. What's the difference between this constant multiple rule and the one from calculus 1? Not much. Just one, instead of having two integrals, you have one integral. And then now as we understand this transition, how we have transitioned from dimension 1 to dimension 2, now we are in the place where that understanding that raising dimension, what does it do to everything, is to be used. And the answer is not much. So you can just look at these and imagine what's going to happen. What's going to happen to when we try to have the same rules for dimension 3 for triple integrals. And the answer will be what? Every integral will be, instead of double, will become triple, okay? Or, just for convenience, it's just a letter, but I will replace it with V, because the domains will be boxes, not rectangles. And that's it. Nothing else matters. The rules will be exactly the same. So sum rule, constant multiple rule will be still available. Okay, there is more to it. There was one more rule. It is the additivity rule, which is not the same as sum rule, and that is what you do when you add the domains, and that rule once again applies. Okay, so in the dimension 1, we added the two domains. How? By two integrals consecutively attached to each other on the right. In dimension 2, or double integrals, the domains are rectangles, and we took two rectangles adjacent to each other as the simplest case of the additivity rule. And now what's going to happen for triple integrals? What would this rule look like?
It would be the same, just have three integrals.
Triple integrals? No, not three integrals. Triple integrals.
No, I mean three intervals.
Integral signs, okay. And what's going to happen here? Rather here?
Yeah, three intervals.
Yeah. What about the domains? So the domains were added together, being two rectangles adjacent to each other, and they were added together. And while you add together the domains, the integrals are also added together. Okay, so if you just use those words, it is clear what's going to happen for triple integrals. What? The domains are
Boxes, the products of three
yeah,
integrals.
yeah. So I'll have here 3, 3, and 3, indicating the rectangles. And once again, I could pick one of the dimensions to be to split it along, or rather cross, such as a fixed x dimension to cut that rectangle into two. This time I have boxes, and so I have boxes. So once again, I'm talking about two adjacent boxes rather than two rectangles like this. Two integrals, dimension 1, two rectangles like this, boxes like this. They adjacent, and once again, they have in common something that is negligible as far as volume is concerned. What they have in common is like a rectangle. So the two rectangles, they overlap by a line, which is negligible as far as the area is concerned. Well, actually, you can start that idea from dimension 1. So in dimension 1, this is what you do to the domains. And what they have in common is this, a point which is negligible as far as the length is concerned. Okay, now we move to dimension 2, and we have two rectangles that have an edge in common. An edge is negligible as far as the area is concerned. Now we're moving to dimension, we move to the next dimension, and we have two boxes, and they overlap by a face, a rectangle, which is negligible as far as the volume is concerned. Okay, so and that's why the addition works out, even though there is an overlap. If there is overlap, it's more substantial, such as two intervals overlapping by like this. okay, then that's not going to work. Same with two rectangles overlapping like this, two boxes that are moved into each other, that overlap will be double counted. And so then the additivity rule does not apply in that sense. So we have to watch out for that. Okay, so otherwise everything works out. The additivity, sum rule, constant multiple rule, additivity rule, even mean value theorem would be also true. One concept I want to bring up now, rather than going through these rules, and that is, I have a few minutes left, the average value value of a function. Remember what that is? Going back to numerical situation, y equal f of x. Average value of function y equal f of x on an integral ab. Remember what that is? How do we average value of functions that vary continuously?
Is it the integral from a to b over b minus a?
That's right. So we take our integral and we divide it by the length of the intervals. So in other words, you can interpret it as if, once again, you have some kind of sandbox and you flatten it. Okay? So then this is the average value. Average value. So it makes sense. So you have that's as much sand in the sandbox, and then but you need only one value. You don't want to worry about with this curvy top of the sand. So what you do, you pick this one as a substitute. Okay. So once again, you divide the integral by the length, and now if we move on to dimension 2, z equal f of xy on AB cross CD. Okay, so what is the average? Once again, think sandbox, but now this time it's a three-dimensional sandbox, like this. The amount of the sand will be the integral over this rectangle, double f dA. Okay, and then what you divide by?
The product of the two units.
The product of the two, or what is important to note is that this is the area of. So in either case, you're looking at the base. Either it is an integral or it is a rectangle at the base of the sandbox is what we divide by. Okay, so we'll do this next time.